Chapter 7, Chemical Reactions. In this chapter, we will look into the basics of chemical reactions, how to balance the chemical equation, as well as stoichiometry. A chemical equation is a notation chemists use to represent a chemical reaction. It consists of chemical formulas separated by an arrow. The starting material in any chemical reaction are reactants. The substance present after the reaction has been carried out are products. By convention, we place all reactants to the left of the arrow in a chemical equation, and we place all products to the right of the arrow. In most chemical reactions, chemical bonds in the reactant break and new bonds form as the product are created. All the atoms present before a chemical reaction begins are still there after the chemical reaction is finished. What is different after the reaction takes place is the way those atoms are connected to one another. Thus, during the reaction, the atoms in the reactant has been rearranged to become products. In the thermite reaction, we have the reactants listed on the left-hand side, and we have the product listed on the right-hand side of the arrow. So when we read the chemical reaction, we read it as iron oxide reacts with aluminum, give iron and aluminum oxide. The letter written in parentheses after each substance tells the state of each substance. For example, H2O followed by a L. This L indicates that this is a liquid water. Down below, we have iodine followed by a letter G. G indicates the iodine is in the gas phase. Most commonly, we'll have S for solid phase. However, when a solid that dissolved in water, we often write AQ to indicate it is an aqueous solution. Aqueous is not a phase of matter like solid, liquid, or gas, so we use the term state instead. The coefficient in front of each substance tells how many units of each substance there are before and after the reaction takes place. The 2 in front of aluminum and in front of iron indicate the numbers of atoms present before and after the reaction. If there's no coefficient, it is understood to be number 1. In the thermite reaction, 2 atoms of aluminum react with 1 formula unit of iron oxide to produce 2 atoms of iron and 1 formula unit of aluminum oxide. The law of conservation of mass states, in any chemical reaction, matter is neither created nor destroyed. This law requires equal numbers of each atom on the 2 sides of any correctly written chemical equation, because we can't create new atoms and we can't destroy atoms in a chemical reaction. All the atoms present before a chemical reaction are present after the reaction is over. A balanced chemical equation will obey the law of conservation of mass. The number of atoms of each element on the reactant side will equal to the number of atoms of that element on the product side of the equation. If we counted for the thermite reaction, on the left-hand side, on the reactant side, we have 2 iron, and then we also have 2 iron on the right-hand side, the product side. On the left-hand side, we have 2 aluminum atoms. On the right-hand side, we have 2 aluminum atoms. On the left-hand side, we have 3 oxygen atoms. And on the right-hand side, we have 3 oxygen atoms. Because these numbers are equal, this is a balanced chemical equation. Let's consider the unbalanced chemical equation for the formation of rust from iron and oxidant gas. An unbalanced equation such as this one is missing coefficients or it has incorrect coefficients. We balance this reaction by first looking at how many of each atom is on each side of the unbalanced equation. On the left, we can tell from the chemical formulas that we have 2 atoms of oxygen and 1 atom of iron. On the right-hand side, we have 3 atoms of oxygen and 2 atoms of iron. Let's start adjusting the equation by adding coefficients in front of any reactant or product. For example, we could balance the iron by putting the coefficient 2 in front of the reactant iron like this. The iron is now balanced. There are 2 iron atoms on each side, but the oxygen remains unbalanced. Adding a coefficient in front of one substance may not be enough to balance the equation, so we have to continue adding coefficients. The oxygen is tricky because we cannot simply put the number 2 in front of the O2 molecule to balance it. That would give us 4 oxygen atoms on the left and 3 on the right. Instead, we can try putting the number 3 in front of the reactant oxygen molecule like this. This does not balance the equation, but it does give us 6 oxygen atoms on the left side. Because there are 3 oxygen atoms on the right, let's add a coefficient 2 on the right side to balance the oxygen atom like this. Now there are 6 oxygen atoms on each side, 2 times 3. But unfortunately, the iron is no longer balanced. There are 2 iron atoms on the left and 4, 2 times 2, iron atoms on the right. Since the iron is unbalanced, so we have to change the 2 to a 4 in front of the iron. Now we have 6 oxygen on the left, 6 oxygen on the right, 4 iron on the left, 4 iron on the right. The equation is now balanced. When balancing a chemical equation, we add coefficients in a trial and error fashion until we obtain a balanced equation. It is important to understand, though, that we can never change the subscripts in a chemical equation in order to balance that equation. Keeping track of how many atoms are on each side of the equation is a useful way to balance equations. As shown in this picture, we have 4 iron on the left, 4 iron on the right, 6 oxygen on the left, and 6 oxygen on the right. They're both balanced. Let's consider a balanced chemical equation from a few different perspectives. The first perspective is the atomic scale. It is useful when imagining the reactants as structures moving through space, perhaps colliding and forming the new structures that are the products. On the atomic scale, we can visualize how water is converted to hydrogen and oxygen by imagining the collision of 2 molecules and the formation of products as the atom change bonding partners. As illustrated below, the red balls represent the oxygen atoms, and the white balls represents the hydrogen atoms. When the 2 molecules of water collide into one another, they form 2 hydrogen molecules and 1 oxygen molecule. Although we can imagine our 2 water molecules floating around, bumping into each other and possibly undergoing a chemical reaction, but 2 water molecules is not a number that we could work very easily in a laboratory. So here comes the more practical, real-life perspective of chemical reaction, the laboratory scale. In the laboratory scale, we must deal with extremely large numbers of atoms or molecules. Luckily, we can use the mole to keep track of the huge numbers of atoms and molecules in a chemical reaction. The mole here is a counting device that helps us to think on a macroscopic scale. Recall that 1 mole of substance contains 6.02 times 10 to the 23 particles of that substance. When thinking on an atomic scale, we imagine two molecules of water interacting with one another and undergoing a reaction that creates two molecules of hydrogen and one molecule of oxygen. In contrast, when thinking on a laboratory scale, we imagine 2 moles of water molecules reacting to form 2 moles of hydrogen molecules and 1 mole of oxygen molecules. The beauty of a balanced chemical reaction is that the ratio of reactant and products to one another is the same regardless of the scale. Using the laboratory scale, how do we measure out a mole of something? We can measure mass in the laboratory by using a balance, so we need to find a way to convert moles to mass. On the periodic table, the molar mass is the number below the element symbol. As the name implies, molar mass is the number of grams of an element in 1 mole of that element. We can represent molar mass in a number of ways. For example, the molar mass of radon, element 86, is 222 grams per mole. That means that 1 mole of radon atoms has a mass of 222 grams. Molar mass is written in several ways, as illustrated to your right. We can find the molar mass of any compound by adding up the molar masses of everything in the chemical formula. Let's take a look at an example here. Find the molar mass of iron oxide. From the formula Fe2O3, we know that it contains 2 atoms of iron and 3 atoms of oxygen. From the periodic table, we find the molar mass of iron is 55.85 grams per mole, and oxygen is 16.00 grams per mole. You simply multiply by the number of atoms of each and sum them up to give you 159.7 grams per mole for the molar mass of iron oxide. Here is another example for aluminum oxide. Aluminum oxide contains 2 atoms of aluminum and 3 atoms of oxygen. Aluminum molar mass from the periodic table is 26.98 grams per mole. Oxygen is the same 16.00 grams per mole. You multiply the molar mass by the number of atoms of each, and then sum them up to get 101.96 grams per mole for aluminum oxide. Stoichiometry is a complicated word for a straightforward process. It is a way to use a balanced chemical equation to figure out how much of each reactant reacts and how much product forms. The chemical equation for the preparation of aspirin is shown below. Rather than write the long chemical names for the 2 reactants, we call them simply reactant A and reactant B. The products are aspirin and acetic acid. Whenever we encounter a new chemical equation, the first thing we should always do is to check to see if it is balanced. In this case, we have 11 carbon atoms on both sides, 12 hydrogen atoms on both sides, and 6 oxygen on both sides. The balanced chemical equation tells us how many moles of each reactant are needed and how many moles of each product will form. In this case, the coefficients of all species are 1. From the balanced chemical equation, we can say that mixing 1 mole of each reactant will give 1 mole of each product. How many grams of each reactant do we need to make 1 mole of the product aspirin? To get that information, we have to use the molar mass of each reactant. Try this on your own. What are the molar masses of reactant A and reactant B? See the figure below for answer, along with the molar masses of the two products. Now we have something quite useful. If we mix 102.09 grams of reactant A with 138.12 grams of reactant B, we get 180.16 grams of aspirin and 60.05 grams of acetic acid. We can use the chemical equation to scale up or scale down a chemical reaction. You can simply multiply all coefficients of the balanced equation by a factor of 100 or by a factor of 0.1. Butane gas has the chemical formula of C4H10. It is the fuel found in disposable lighters. When you turn the metal wheel in the lighter, a spark is made and oxygen molecules from the air ignite the gas. This chemical reaction called combustion occurs whenever a fuel such as butane burns in the presence of oxygen to produce carbon dioxide CO2 and water H2O. The given balanced chemical equation tells us that 2 moles of butane react with 13 moles of oxygen gas to produce 8 moles of carbon dioxide and 10 moles of water. The balanced chemical equation calls for 2 moles of butane, so we need 2 moles times 58.12 grams per mole, the molar mass of one butane molecule, equal to 116.24 grams. This mass of butane reacts with 13 moles of oxygen molecules. Using the molar mass of oxygen, we see that 13 moles of oxygen have a mass of 416 grams. The total masses of all reactants and products are calculated below. If we start with 532.24 grams of reactant, and we will produce 534.24 grams of products, we can see that there's no mass gained or lost during the chemical reaction. This must be true because our balanced chemical reaction has equal numbers of each type of atoms on each side. Therefore, mass is conserved and the law of conservation of mass is obeyed. Chemical equations tells us how chemical reaction could happen, but not always how they do happen. Sometimes side products or byproducts form. These products do not appear in the balanced chemical equation. To perform a chemical reaction, you need more than just the balanced equation. You also want to know the detailed directions, like in a recipe. Chemists track the progress of chemical reaction in less dramatic fashion by using reaction energy diagrams, which tell us how the energy of the reaction changes as it progresses from reactants to products. The reaction energy diagram below records energy on the vertical axis and reaction progress on the horizontal axis. The reaction begins at the flat area on the left, and the reactants are poised at the energy indicated. The reaction concludes at the plateau on the right, which marks the energy of the products. During the course of the reaction, the reactants must scale an energy hill to get to the product side. In the reaction energy diagram on the left, the energy of the products is higher than the energy of the reactants. This indicates an endothermic reaction, one that absorbs heat energy. Because an endothermic chemical reaction requires heat energy as a reactant, we can even add the words heat energy on the left side of the balanced equation, although it is technically not a formal part of the balanced equation. Now, consider the opposite situation, depicted in the diagram on the right. In this case, the reactants are higher in energy than the products. This exothermic reaction produces heat energy. We can add the words heat energy to the right side of the balanced equation. Another question that chemists are interested in is how fast will a reaction go? The speed of a reaction is related to the size of the energy hill that the reactants must scale to get to the products. That hill is the activation energy of a reaction. How is the size of the activation energy related to how fast of a reaction goes? To answer this question, we turn to the track, where a high jumper is trying to go up and over the bar. When the bar is set low, the high jumper quickly goes over it, perhaps on the first or second try. But as the bar goes up, the high jumper must try again and again to get over it. Maybe she tries a dozen times and finally makes it. Or maybe the bar is so high that it takes her weeks of practicing and trying to finally make it over the top. Activation energy works the same way. The reactants in the chemical equation may have a small hill to scale, and so they scale it quickly, without requiring much energy. But as the hill gets bigger, the reaction takes longer because fewer reactants have sufficient energy to get to the top of the hill and over to products. Let's consider a chemical reaction that we discussed earlier in this chapter, rusting, a very slow reaction between iron and oxygen. We know that it usually takes quite a long time for iron to rust, but if you live near or have traveled to a coast, you may have noticed that cars are rustier near the ocean. The salt in the sea air makes cars rust faster. Returning to our high jumping analogy, this means that when salt is present, the reaction has a lower bar to get over. In chemistry lingo, we say that the activation energy is lower for the reaction that produces rust when salt is present. The reaction energy diagram for rusting with salt and without salt looks something like these two below. Note that the starting and ending point for the reaction are the same. What difference is the size of the hill? The hill is smaller in the presence of salt, as shown to the right, because salt lowers the activation energy of the chemical reaction, but is not a reactant or product. We refer to it as a catalyst. The rusting reaction can go even faster. If you go to your local sporting goods store, you will find an array of heat packs that can be used as socks or glove warmers for winter sports, or as relief for some sore muscles. Many of these products are based on the rusting reaction, but if you have cold toes, you want this reaction to happen faster than the time it takes for a car to rust. If we urgently want this chemical reaction to proceed, we can speed it up by adding a catalyst to the heat pack. This type of heat pack contains pieces of iron. When you are ready to use it, you open it up to oxygen in the air. If we look at the list of ingredients for these heat packs, we can see that they contain a lot of salt. Because salt is a proven catalyst for this reaction, in its presence, the iron in the pack rusts really fast. It is fast enough to produce heat in seconds. Question 1. How many oxygen atoms are on each side of the balanced chemical equation? The equation is given below with choice A, 7, B, 10, C, 14, D, 17. Please pause your video here. The correct answer is C, 14. On the left-hand side of the equation, there's oxidant gas. Each oxidant gas has 2 oxidant atoms. There are 7 oxygen molecules together, so therefore you have 2 times 7 equal to 14. On the right-hand side, you have carbon dioxide gas. Each carbon dioxide gas has 2 oxygen. There are 4 carbon dioxide molecules, so 2 times 4 give you 8. From the water molecule, each has 1 oxygen. There are 6 water molecules, give you 6 oxygen. If you add everything on the right-hand side together, that'll give you 14 as well. The correct answer is C, 14. Question 2. When the reaction is balanced using whole numbers, which coefficient is needed in front of the carbon dioxide? A, 4, B, 18, C, 14, D, 8. Please pause your video here. So the correct answer is D, 8. Let me rewrite the chemical equation, and I'm going to work this out together with you. So I'm going to omit all the states for simplicity. All right, so let's take a look at this. We have 4 carbons on the left and 1 carbon on the right. Therefore, we need to put 4 in front of CO2 to make 4 carbons. So the carbon is balanced. Then we have 10 hydrogen on the left and 2 hydrogen on the right. We need to put a 5 in front of water to make 10 hydrogens on the right. So hydrogen is balanced. Now we have oxygen. On the right hand side, we have 2 times 4, that's 8. And then there are 5 from water, that gives a total of 13 oxygen on the right. But on the left hand side, we only have 2. Therefore, we can multiply the left hand side by 6.5. I know the 6.5 is a little weird. As you know, we usually don't keep a decimal for coefficient. But by multiplying by 6.5, you have 13 oxygen on the left. Now, we can scaling this up to make a whole number coefficient. So I'm going to multiply the entire equation by 2. Okay, now I will have 2C4H10 plus 2 times 6.5, that's 13. O2 give you 8 CO2 plus 10 H2O. Okay, let's check our answer. So on the left hand side, we have 2 times 4 carbon, that's 8. And then on the right hand side, we have 8 carbon. So they're balanced. And then on the left hand side, we have 2 times 10, that's 20 hydrogen. And then on the right hand side, we have 10 times 2, we have 20 hydrogens. So the hydrogens are good. Now let's look at the oxygen. 13 times 2, that's 26 oxygen atom on the left. And then on the right hand side, we have 2 times 8, that's 16. And then this is 10 oxygen, that's 26. So they're equal. So the entire equation is considered balanced. To answer the question, you look at the coefficient in front of carbon dioxide on the right. So the answer is 8, carbon dioxide. Question 3. What is the correct way to rate this chemical equation? A. 2 moles of propane react with 10 moles of oxygen to form 6 moles of carbon dioxide and 8 moles of water. B. 2 propane molecules react with 10 moles of oxygen to form 6 liters of carbon dioxide and 8 grams of water. C. 2 liters of propane reacts with 10 grams of oxygen to form 6 liters of carbon dioxide and 8 grams of water. D. 2 grams of propane reacts with 10 grams of oxygen to form 6 grams of carbon dioxide and 8 grams of water. Please pause your video here. The correct answer is A. 2 moles of propane react with 10 moles of oxygen to form 6 moles of carbon dioxide and 8 moles of water. The letter written in parentheses after each substance tells the state of each substance. G for gas, L for liquid, S for solid, AQ for aqueous. Therefore, there's no liters or grams involved when you talk about this chemical equation, so the correct answer is A. They're all related by the molar ratio. Question 4. What is the molar mass of sodium carbonate, Na2CO3? A. 83.00 grams per mole. B. 105.99 grams per mole. C. 130.01 grams per mole. D. 51.00 grams per mole. Please pause your video here. The correct answer for this question is B. 105.99 grams per mole. Let's work this problem out. You first find the molar mass of sodium from the periodic table. It is 22.99. Then carbon from the periodic table is 12.01. Oxygen, it is 16.00. From the chemical formula, there are 2 sodiums. So you can multiply sodium by 2 to get 45.98 grams per mole. Then there's only 1 carbon, so you have the same 12.01. Then you have 3 oxygens, so it gives you 48.00 grams per mole. You're going to sum everything up to get 105.99 grams per mole. Question 5. If 10 moles of octane reacts with an excess amount of oxygen, how many moles of carbon dioxide are formed? A. 80 moles carbon dioxide. B. 320 moles of carbon dioxide. C. 160 moles of carbon dioxide. D. 20 moles of carbon dioxide. Please pause your video here. The correct answer is A. 80 moles of carbon dioxide. From the balanced chemical equation, we know that every 2 moles of octane will give you 16 moles of carbon dioxide. We can set 2 conversion factors as 2 moles C8H18 for every 16 moles of CO2, or 16 moles of CO2 for every 2 moles of C8H18. The question begins with 10 moles of octane, so we have 10 moles C8H18. We multiply by the conversion factor on the right, because we want to cross out the moles of C8H18. We're going to put it on the bottom. Then the unit we want, we're going to put it on the top, so that we can cross out the moles of C8H18, and then we're going to end up with the moles of CO2. If you punch in the numbers into the calculator, you will end up with 80 moles of CO2. Question 6. Use the law of conservation of mass to determine the mass of oxygen gas that must react with 256 grams of elemental sulfur S8 to produce 640 grams of sulfur trioxide, according to the following equation. A. 32 grams of oxidant. B. 384 grams of oxidant. C. 897 grams of oxidant. D. 256 grams of oxidant. Please pause your video here. The correct answer is B. 384 grams of oxidant. We first need to determine the molar mass of each species. So, elemental sulfur is S8. From the periodic table, sulfur is 32.07. There are 8 of them. That gives you 256.6 grams per mole. Next, we have oxygen gas. Oxygen is 16.00 each. There are 2 of them. Gave you 32.00 grams per mole. Lastly is SO3 with only 1 sulfur, 32.07 times 1 plus 3 oxygen at 16 each. That gives you 80.07 grams per mole. From the question, we want to have 256 grams of elemental sulfur. Okay? This is about a mole of sulfur. From the balancing equation that we know every 1 mole of sulfur, S8, will react with 12 moles of oxygen. So the ratio is 1 to 12. Therefore, if you know 1 mole of oxygen is 32.00 grams for every 1 mole, and we have 12 moles of oxygen, you can simply just multiply each other to give you an answer of 384 grams of oxygen needed. There is a much easier way to solve this question. By using the law of conservation of mass. The law states that in any chemical reaction, matter is neither created nor destroyed. In other words, the total mass of all reactants is equal to the total mass of all products. Therefore, 256 grams of sulfur plus a question mark amount of oxygen equal to 640 grams of SO3. You just have to solve the question mark by using 640 minus 256, which equals to 384 grams of O2. Question 7. How is energy transferred in chemical reactions? A. Energy is absorbed in endothermic reactions, and energy is absorbed in exothermic reactions. B. Energy is released in endothermic reactions, and energy is released in exothermic reactions. C. Energy is released in endothermic reactions, and energy is absorbed in exothermic reactions. D. Energy is absorbed in endothermic reactions, and energy is released in exothermic reactions. Please pause your video here. The correct answer is D. Energy is absorbed in endothermic reactions, and energy is released in exothermic reactions. Remember that endothermic reaction absorbs heat, so the heat energy is part of the reactants. On the opposite side, exothermic reaction produce heat. Heat energy is on the product side. Question 8. What is the energy required for a chemical reaction to scale the energy hill? A. Activation energy. B. Endothermic energy. C. Exothermic energy. D. Hill energy. Please pause your video here. The correct answer is A. Activation energy. This is more of a definition question. Regardless, you have an endothermic scenario or exothermic scenario. You have this or this. The distance from the peak to here are called activation energy. There's no such term endothermic energy, exothermic energy, nor Hill energy. Question 9. Select the statement that describes the energy diagram. A. The energy diagram shows an endothermic reaction because the reactant energy is higher than the product energy. B. The energy diagram shows an exothermic reaction because the reactant energy is higher than the product energy. C. The energy diagram shows an endothermic reaction because the reaction energy is lower than the product energy. D. The energy diagram shows an exothermic reaction because the reactant energy is lower than the product energy. Please pause your video here. The correct answer is B. The energy diagram shows an exothermic reaction because the reactant energy is higher than the product energy. So let me first label reactant on the left and then the product on the right. From the diagram, you can clearly tell that the energy of B is lower than the energy of R. Therefore, we can rule out C and rule out D. Since the product is at a lower energy compared with a reactant, the energy has been released in the reaction. When you have the energy released, it is called an exothermic reaction. Therefore, choice B is correct. Question 10. Calculate the molar mass of aluminum nitrate. A. 136.99 grams per mole. B. 88.99 grams per mole. C. 213.01 grams per mole. D. 165.01 grams per mole. Please pause your video here. The correct answer is C. 213.01 grams per mole. The trickiest part of this question is to figure out how many atoms of each kind of element are in the chemical formula. So let's begin by writing down the molar mass of each atom first. Aluminum is 26.98. Nitrogen is 14.01. Oxygen is 16.00. Obviously, there's only one aluminum, so you multiply by 1, you have 26.98 grams per mole. Nitrogen. So remember that I'm going to put in a different color. There is a 3 outside the parentheses. You need to multiply everything by 3. Okay, so you will have 3 nitrogen. What about oxygen? You're going to do the same. 3 times 3, so you can have 9 oxygen. So if you multiply this, you have 42.03 grams per mole, and then you have 144.0 grams per mole. If you add them all up, you will end up with 213.01 grams per mole. This is choice C.